So this is chapter 6, part 4. So we're going to talk about oxygen usage and tolerance patterns in microbes. So again, you want to use a lot of these words, and kind of think of them as terminology. So if you're into flashcards, flashcards could be helpful here throughout this chapter. So first we're going to talk about aerobes. So you want to be really careful when you're reading the questions and anything related to this, and note whether it's aerobes or anaerobes. Aerobes have to do with liking oxygen or oxygen itself, and anaerobes is the opposite. Okay, they don't prefer oxygen, generally speaking. There's kind of exceptions to the rule as we go through this, but generally speaking. So aerobes can use oxygen in their metabolism, so they like it and they can use it and possess the enzymes that are needed to process those toxic oxygen products I mentioned earlier. So if they didn't have those enzymes, if it was a microbe that did not have those enzymes available, then it wouldn't be able to process those byproducts. But in this case, aerobes do. So an organism that cannot grow without oxygen is an obligate aerobe. So an obligate aerobe requires oxygen to grow. So that's another term there. It's just not bolded. Okay. Examples of aerobes include most fungi, protozoa, many bacteria, specifically Bacillus species and Mycobacterium tuberculosis. Microaerophiles. Let's look at this word, see if we can kind of judge what it means. Micro being small, aero being oxygen, and then philes being the type. Okay, so microaerophiles are harmed by normal atmospheric concentrations of oxygen, but do require a little bit of oxygen in its metabolism. So if it was living in normal atmospheric concentrations of oxygen, then that would be harmful to it. But the microbe does require just a little bit of oxygen in its metabolism. Examples that live in the soil or the water, not directly exposed to the atmosphere: H. pylori and Borrelia burgdorferi. So you can see here, okay, so these tubes are a liquid thio, probably, and it's showing, the microbes have been inoculated into this broth, this broth media, and when the microbes grew, they grew up towards the top, closest to the source of oxygen, which would be if there's a little bit of air underneath that cap. Just like any jar or whatever has a little bit of air where you screw it shut. So those microbes are all the way up there so it can get to the oxygen. So that tells us, when we look at this in the lab, if we've inoculated this with a pure culture and that pure culture grows all the way towards the top, then that tells us that that is an aerobe. Right? Now we know that that is an aerobic organism. And it's a thin layer at the top. If we have this thick layer that kind of spans a little bit, then we know that this might be a microaerophile. And there are specific bacteria that fall under that category and that grow this way in one of these tubes of thio media. All right, so a facultative anaerobe, now we're at anaerobes, okay? A facultative anaerobe do not require oxygen for metabolism, but will use it if it's present. So they're like, yeah, I could take it or leave it, but if it's here, I'm going to go ahead and use it. And so what you end up seeing is growth throughout the tube. Now, this picture doesn't really show it the way I would like it to. I would like to see, growth all the way through, but it's able to grow throughout the tube because it can take it or leave it. Examples: many gram-negative intestinal bacteria and also staphylococci. anaerobes. Now we're just talking about anaerobes. These guys lack the metabolic enzyme systems for using oxygen. So there's a couple of different scenarios here, but first I'll say if it's an anaerobe and it grows like this, you don't see any growth at the top of the tube. Remember, this is a liquid type media here, and all the microbes migrate down to the bottom and kind of hide away from that oxygen that's up there. So most of the growth is going to be down here. Okay, so if we had a tube like this in the lab and we saw all the growth down to the bottom, then we would call that an anaerobe. An obligate anaerobe is a microbe that specifically must live in the presence of no oxygen. All right, so it lacks the enzymes for processing toxic oxygen and will actually die in its presence. So oral bacteria and intestinal bacteria are both obligate anaerobes. It requires an anaerobic environment. Aerotolerant anaerobes. So look at the word, aero, oxygen, tolerant. It is tolerant. So anaerobes that are tolerant of oxygen do not utilize oxygen, but will survive and grow to a limited extent in its presence. It's not going to use it to grow, but it's not going to kill it. All right, so it's not harmed by oxygen, mainly because they possess alternate mechanisms for breaking down peroxides and superoxide. Examples, lactobacilli, streptococci, and clostridial species. And you can see there is solid growth throughout the whole tube. It doesn't really care. It's going to grow wherever in these tubes. All right, so moving on, carbon dioxide. So organisms that grow best at higher carbon dioxide levels would be referred to as a capnophile. Okay, so again, terminology here. Make up your list or your flashcards to remember these. So Neisseria, Brucella, and Streptococcus pneumoniae are all examples of capnophiles. pH, defined as the degree of acidity or alkalinity of a solution, expressed from 0 to 14 on the pH scale. 7 is neutral and is what pure water should be as far as pH. And as the pH value decreases, goes down from 7 to 6 to 5 to 4 to 3, and so on. Towards 0, the acidity increases. So the lower the number, the more acidic something is. So if something has a pH of 1, then you know that that is very acidic. And as the pH value increases, 8, 9, 10, 11, 12, 13, 14, the alkalinity increases. So the majority of organisms live or grow in habitats between a pH of 6 and 8. However, there are extremes. So one example is an acidophile. They thrive in acidic environments. Euglena mutabilis, Thermoplasma, and Picrophilus. These guys like acidic environments. The first one grows, the Euglena mutabilis, grows in acid pools from 0 to 1, right? That's pretty acidic. Then we have, most molds and yeasts tolerate acid and are common spoilage agents of pickled foods. Alkalinophiles are organisms that thrive in the opposite end of the pH spectrum, so more alkaline conditions. Natronemonas live in hot pools and soils up to a pH of 12. Proteus can create alkaline conditions to neutralize urine and colonize and infect the urinary system. So Proteus is a common culprit of urinary tract infections, as well as E. coli. Osmotic pressure. Osmophiles live in habitats with high solute concentration or a bunch of solids. Okay, when we say high solute concentration, it means it's very concentrated. Halophiles prefer high salt concentrations. Obligate halophiles, Halobacterium and Halococcus grow optimally at 25% sodium chloride, but require at least above 9% sodium chloride. So that's kind of mind-blowing when you think about that. Facultative halophiles, remarkably resistant to salt, even though they do not normally reside in high salt environments. So they'll put up with it, whether they like it or not. And then Staphylococcus aureus can grow on sodium chloride media ranging from 0.1% all the way up to 20%. So Staph aureus likes that salt content as well. Radiation, phototrophs use visible light rays as an energy source, and non-photosynthetic microbes tend to be damaged by toxic oxygen products produced by contact with light. Ultraviolet and ionizing radiation can be used in microbial control, and you've probably seen that if you've ever had your nails done. You know that a lot of times they'll take the instruments that they use to make your nails beautiful. They'll put them under UV light, and then there's, sometimes they'll use autoclaving in certain instances as well. But pressure, barophiles, these guys love pressure. They thrive under it, and they exist under pressures that range from a few times to over 1,000 times the pressure of the atmosphere. So they can survive very deep in the ocean and so on. Other organisms in all but the rarest instances, microbes, live in shared habitats. So we're going to talk a little bit about partnerships. So, and I guess I will stop here and pick up on the last part of this chapter next, because I don't want to rush through this.